Okay, let's continue our discussion further. So we were looking at the solutions of Callan-Zemanzik equation. And were interested in the behavior of the solution in the limit of large momenta. Okay, when we scale all the external momenta by some large factor, how the solution behaves in such a case, that is what was our interest. The behavior of the solution for large external momenta. Okay, so let me quickly summarize what we have done so far. So we introduced a variable t, okay, with which we scale the external momenta, and then we had equation which describes how the Green's function, the renormalized Green's function, the differential equation that renormalized Green's function obeys. Okay, so we had found that t delta over delta t plus beta tilde lambda r, okay, del over del lambda r, so renormalize couplings. Okay, so today's discussion, in fact, most of the discussion has not been very specific to 5-4 theory. Okay, so this is, the discussion is more, it's applicable to other theories as well, because I am not assuming anything really specific to 5-4 theory in this discussion. So I am just saying that there is some coupling constant which is dimension less than 4 dimension, and there is some other parameters, for example a mass parameter which is dimension full. Okay, and this is the equation that describes the behavior of Green's function with change in the value of t. Okay, this acting on G tilde, this is what we had written last time. Okay, this is equal to 0. And then we search for the solution, and in order to find the solution, you recall that we had to introduce running coupling and running mass. So I had also introduced this running coupling constant. Saying constant is not a good idea. Running coupling, this is a constant, lambda r at a fixed mu, that's a constant. And running coupling was defined by this equation together with its boundary condition. Okay, and the boundary condition was that lambda r at t equal to 0 is same as lambda bar, the running coupling at t equal to 0 is same as lambda r. That was the condition. And this is the defining equation for the running mass. Okay, where the boundary conditions are Okay, so I never put a subscript r on the running mass parameter and the running coupling. Okay, here only for the renormalized couplings and renormalized masses I put r. And then we found the solution. Okay, I should also remind what is gamma tilde m and gamma tilde phi. So gamma tilde m is 1 plus gamma m, and gamma tilde phi is d phi tilde plus gamma phi. Okay, and remember mu is always fixed. So what was the solution? Solution was the following: g tilde n, or this Green's function, at scaled external momenta, where each external momentum is scaled by a factor of e to the t, okay, is given by the following: g tilde n r. So here you have everything else fixed, right? So you have chosen a particular mu, okay, and correspondingly you have a mr, which is a function of mu, but mu is fixed, so mr is fixed and lambda r is fixed, and you are just varying t, okay, which means you are just changing the scale of the external momenta, okay, by choosing some value of t, and that you can calculate, find by looking at Green's function at some fixed momenta pi. But now you calculate that Green's function not by putting lambda r, mr and mu, but rather putting lambda bar at value t. Okay, so the running coupling at t, then m bar at t and mu. Okay, and then you have to multiply this exponential factor. Okay, so this is what we have found last time. And then we also saw that if you we have also seen that if you put beta tilde equal to 0, put the beta function to 0, and put gamma tilde m to 1, gamma m tilde to 1, which means you are putting gamma m to be 0, okay, and you put gamma tilde phi to be d phi tilde, which means you have put gamma phi to 0. Okay, you have put the anomalous dimension for phi to be 0, okay, so that gamma tilde now takes the value which is equal to canonical dimension of phi tilde, okay, canonical dimension meaning the mass dimension, okay, and similarly if you put the gamma m to be 0, then gamma tilde m is 1, because gamma tilde m is 1 plus gamma m, okay, and yeah, I mean this is when the case when you have all the z's to be equal to 1, okay, there are no infinities and you are not doing any renormalizations. Then in that case g tilde n r, that is something we saw last time, it becomes g tilde n pi lambda r pi tilde. Okay, you can, so think of this e to the t as some s. So you are scaling all the pi's by a factor of s. Then g tilde n is without any s factor multiplying the external momenta, but the masses are divided by a factor of s, the mRs. Okay, and then you have an s power nd phi tilde. Okay, and that is what you would expect based on a naive dimensional analysis. Okay, naive power counting, that how many powers of, what is the dimension of this g tilde. Based on that, this is what you would expect. But this expectation is true if you do not get any, you do not include any corrections coming from the field theory. Okay, no loops are included in this. You have put all those effects to 0. And of course, that is not true in general. You will have to include all these quantum effects, and you will have singularities in these loop integrals. So also let's understand this factor. Okay, here what this is saying is, if you look at this piece, this left hand side, you have scaled up all the external momenta by some scale. Okay, so now some large scale, so you have very large external momenta. Okay, which is same as saying, keeping the momenta fixed, you scale down all the mass parameters. Okay, here mr you scale down to a factor of 1 over a factor of 1 over e to the t. Okay, so that's what you are doing, and they are equivalent because, you know, when external momenta are very large, then these mass parameters that you have, okay, they do not, they become effectively very small. So either you see it this way or that way. Both are same. Okay. So above result is consistent with our naive power counting. Okay, and we will get, as I said, corrections from renormalization effects. Okay. Now, before we proceed further in analyzing the behavior at large t for these Green's functions, let us look at the equation of the running coupling. Okay. So up to here, this is we had already done. So let's look at first the equation of running coupling constant, and that will be useful in analyzing behavior at large t. So we had delta lambda bar t lambda r over delta t is equal to beta tilde lambda bar t lambda r. Okay. Now we will integrate this from some time, from some value of t which we will take equal to 0 to some value of some non-zero value of t. So let's integrate this. So we have d lambda bar t prime lambda r over beta tilde lambda bar t prime lambda r. Okay, it's integral over dt. Let's put it prime, all of them prime. So t prime equal to 0 to I'll just omit this, from 0 to t. Okay, and here I should have lambda bar. So here the integration variable is lambda bar. Okay, lambda bar is what I'm integrating over, and beta tilde is a function of lambda bar. Okay, so when I put the limits, I should put the limit here. So at t equal to 0, you have lambda bar of 0 lambda r, and here lambda bar of t lambda r. Okay, these are the integration limits, which is just t. Okay, so that's the expression that we get. Now note that from here we immediately conclude that if beta tilde of lambda bar is equal to 0 for some value of lambda bar, okay, then t will diverge, then t will be infinite. Your integrand, which is 1 over beta tilde, that is becoming 0. Okay, so integrand is becoming divergent. So your t will be infinite. Okay. Okay, so we will have more to say about these values of lambda bar for which beta tilde becomes 0, meaning the beta function becomes 0. Okay, we'll discuss more about this. But at this point, I also make a note of the fact that beta tilde of 0, meaning beta tilde at lambda bar equal to 0. So I'm putting the running coupling constant to be 0, and beta function at 0 is just 0. Okay, that I mean, this is true because you see the beta tilde or the beta function gets its contributions from Feynman diagrams. Right? You calculate these loop diagrams, and that is from where it gets these contributions. And if you write Feynman diagrams, they all bring some powers of the coupling constant. Okay, so if you have a Feynman diagram like this, I am drawing in 5-4 theory. So this brings a power of lambda r square. Okay, and so forth. So if you draw up to some particular order in lambda, then you will have a polynomial of some order in lambda r. Okay, and if you put lambda r to be 0, that polynomial will vanish. Okay, because there are no constant terms. There is no way you generate a constant term, right? Because these diagrams always come with the overall factors of lambda to the something, lambda r to the something. So beta tilde will be 0 at origin. Okay, so this is also the other way you can say is that if you put all the couplings to 0, okay, then the beta tilde, the beta function will be just 0 because there are no corrections now. Okay, so I'll do a slight modification, not really necessary, but probably it will be helpful, that I don't use lambda, which I have been using for the 5-4 theory. Instead, I will use G. Okay, G will denote a coupling constant, a dimensionless coupling constant. Okay, so that we can free ourselves from this 5-4 theory. Okay, so I'll just use G to denote coupling, so that we never confuse that we are really talking about 5-4 theory. But it's not necessary that I should do it. So Okay, by reserved for 5 to the 4, meaning I had reserved for 5 to the 4. It's not that everyone has. So I will use G instead of lambda, okay, for the coupling, for dimensionless coupling in 5/4 theory. Sorry, for dimensionless coupling in 4 dimension. Okay, so slight change of notation. Okay, so let's go back, and so as I said that if beta tilde vanishes for some value of lambda, then this T is infinite. Okay, meaning you have okay, let's see what it means. So suppose beta tilde of G bar. Okay, now G bar is the running coupling. Okay, instead of lambda bar I am writing G bar. Suppose beta tilde G bar, that is equal to 0 only for G bar equal to 0. Okay, not otherwise. So beta tilde vanishes only when the coupling constant vanishes. Okay, the running coupling vanishes, or equivalently the coupling constant vanishes, and further it is positive otherwise. Okay, so except for the origin, it's positive everywhere. So the form is of this sort. So beta tilde of G bar, this is G bar, and beta tilde at the origin is 0, and it is always positive, so it has, let's say, this form. Okay, now dg bar, meaning change in the value of coupling, running coupling, is equal to beta tilde G bar. Okay, when we do a beta tilde G bar dt, so when we do a small change in the value of t by a positive amount dt, dg bar is beta tilde times dt. So you see that the change is positive if you increase the value of t. Okay, so you see that G bar of t keeps increasing, okay, and it goes to infinity as t goes to infinity. Okay, so you do it successively, repeatedly, and because beta tilde is positive for all values of g or all values of G bar, okay, that's suppose that's given to us in a particular theory, then in that theory G bar will keep increasing as you increase t, and in the limit t goes to infinity, G bar will go to infinity, and t going to infinity is the ultraviolet limit. Okay, because if you make all the t's very large, it means you have scaled up, you have made all the external momenta very large. Okay, so you are really in the ultraviolet limit. It's called ultraviolet limit. And similarly here for the same case where beta tilde is positive, like what I've given here, then G bar of t goes to 0 as t goes to minus infinity. Okay, and t going to minus infinity is the infrared limit. All the external momenta are very small. Remember, we have multiplied with e to the t. So e to the t with t negative is a very small number. So we are really making all the external momenta very small. And now the running coupling that you should use in the right hand side of this. Okay, now here I have put already here. Okay, that's what I'm calling G bar now. That's going to 0. Okay, but if you scale up to large momenta, then the coupling, running coupling is becoming infinite, very large. The other possibility is that suppose beta tilde of G bar is equal to 0, again only for G bar is equal to 0. So that's an assumption. Suppose this is what happens in some theory. And beta tilde of G bar is negative. Suppose that is also given to us. Okay. Otherwise, in all other values it's negative except for the origin. So it looks like this. Here I have G bar and here I have beta tilde of G bar. So at the origin it is 0 and then it is negative. Okay, then what happens? Following exactly what I said in the previous case, you can see that G bar of t goes to 0 as t goes to infinity. So meaning as you take the ultraviolet limit, meaning take very large t, the coupling constant becomes very small. The running coupling constant becomes very small. Okay, and that's a very good situation. If the coupling constants are becoming very small, okay, and as I had remarked earlier, if the coupling constants are becoming very small, okay, then this on the right hand side, the Green's function that you have to evaluate, you don't have to go to very higher orders in the coupling constant. Okay, suppose you want to calculate 4-point Green's function. Okay. Now, if coupling constant or the running coupling constant is not very small, then to have a good estimate of this 4-point Green's function, you should go to some reasonably high orders in perturbation theory. Okay, so you should draw lambda r squared, lambda r square diagrams, lambda r cube, lambda r4 or whatever, and go to some higher orders, and then replace those lambda r's by lambda bar, the running coupling. Okay. But if it so happens that the value of the running coupling is very small, then you do not really gain by including very high order terms, right? Because they are going to be becoming small very rapidly. Okay. The moment you go to a higher power of a small number, it becomes very small. Okay, so that is the advantage. You can get good predictions by even while you keep your calculation only to lower orders. So okay, and in this situation, in this case, you also have G bar of t that goes to infinity as t goes to minus infinity. That's in the higher limit. Okay, and because the coupling constant is becoming large here, you cannot rely anything. You cannot rely on the perturbation theory, right? Because perturbation theory can tell you something only when the coupling constants are small. Because otherwise, what you are throwing away, the diagrams that you throw away and do not calculate, are much larger than what you are keeping. Right? So, just to give you an example, suppose you are calculating 4-point function. So you calculate this and other corresponding diagrams at order lambda r square, but then you also have these ones. Okay, many more you can. So you have many more powers of lambdas. Okay. Now, if usually you will either stop at this level, this order, or some order, or even let's say at this order, but you are then not including other higher order terms, okay, which still have higher powers of lambda r. Okay, and the reason you do not keep is that what you are throwing is smaller, much smaller compared to what you are keeping, because lambda r is small. Okay, but if lambda r is not small and corresponding lambda r bar or G bar, as I am using now, is not small in the higher limit, then what you are throwing away are actually larger than what you are keeping, right? Because a large number raised to power 2 or power 4 or whatever is larger than, so G square is larger than G if G is greater than 1. Okay? So you are not allowed to stop the perturbation series somewhere if your coupling is not small. Okay, so in that case you cannot use perturbation theory. Okay, so Good. And now a more general situation is the following. So here, I think I should draw like this. Okay, I can take help from here. Okay. Okay. This will be useful. So, a more general situation is okay, like this. So here I have G bar, and here I have the beta function, beta tilde G bar. Suppose this is the behavior. This is the more generic behavior, right? So I have ensured that beta tilde of 0 is 0, because that is something we have already argued that should be the case. Beta tilde of 0 should be 0, so I am starting there. Okay, and the beta function behaves in a certain way. Okay, now let's look at this one. So here beta function vanishes at G1, G2 and G3. Okay, so beta function vanishes at G1, G2 and G3. Okay, we have already seen let me write it down. We have already seen that if beta tilde vanishes for some G bar, some value of G bar, in this case I am just not putting a bar on the top, these are some specific values, but if you wish you can put. So here beta tilde vanishes for G1, G2, G3. These are the values of G bar. Okay, if it vanishes, then the corresponding time is infinite. Then the corresponding t is infinite. Okay, so let's analyze now first things in the vicinity of this G1. Okay, this point. So in vicinity of G1. Okay, so here if you see the G bar is 0 and the slope of beta tilde, okay, that slope here, the slope is negative. Okay, meaning the derivative of beta tilde with respect to G bar, that's negative. Okay, so let me write that down. So here d beta tilde G over d G bar is negative. Okay, slope is negative even though the value it's 0 here at G1. Now you start at some value of running coupling near G1. Okay, let's start here. Let's start here. Okay. Now here, when I start here, let me give it a name. Let's call it GA. Okay. The real thing is G1. I'm just taking arbitrary point GA. Okay. Now here, the value of beta is negative because this is the value of beta. Okay. So value of beta is negative. So when I increase T, okay, then the running coupling G bar should decrease. Right? Let me remind you again. See here, it is this situation. Now we have beta negative, and when I increase T, okay, G bar should decrease. In the limit T going to infinity, G bar goes to 0. Okay, but that was this situation. But in general, because beta tilde is negative, as you increase T, G will decrease. Right? This is somewhere. But anyway, you understand that. It should decrease, okay? So decreasing means these are the smaller values of G bar, right? So as I increase T, I should start moving in this direction. So I start moving. I was here, the beta tilde was here when the running coupling was this was the beta tilde. And as I increase T, I am going along this direction. Okay, so increasing T decreases G bar, and that is why I am going like this. Let's start from here this time. Some lower value of coupling constant, running coupling constant. Okay. You start from here. Now the beta tilde is positive. Okay, and you know that when beta tilde is positive, as you increase T, beta tilde will the running coupling will increase. Okay, because beta tilde is positive, and this is the direction in which the coupling constant is increasing. Right, these are the larger values. So if you start from here, this coupling, you start going along this direction. Okay, and this is for T going to infinity. So you increase T, and when T is infinite, you reach here. You start from here, you start increasing T. When T becomes infinite, you reach here. Okay, let me put it slightly differently. What happened? Okay, just a second. Yeah, I want to beautify a bit. It's becoming too. Yeah. So as I said, it flows to here and it flows to here. These were some starting values. Let's call that GB. So, and this is as okay, it's okay, T goes to infinity, and for this also T goes to infinity. Same for both. Okay, and this is, I'm using this first point. We have already seen that if beta tilde vanishes for some G bar, then the corresponding T becomes infinite. Okay, so when T really becomes infinite, you reach at this point, G1. Okay. Good, now let's analyze things in the vicinity of G2. Okay, let's look at here. So you see that the curve here has a positive slope. Unlike this one, it had a negative slope. The curve has a positive slope here. Okay, so dB tilde beta tilde g bar over dg bar is positive. Okay, so as we increase t, the running coupling moves away from G2, right? Because it's positive, so as you increase t, because the derivative is positive, the change in the value of G2 will be positive. So if you start from here, let's say here, then you go further, you start going away. Okay, and similarly here. So here, and similarly here, if you take, okay, then as you take t going to infinity, you start going to the left, to the lower values of g bar, because your beta tilde is negative in this region. Okay, so because it's negative, it starts going this way, and here it's positive, it starts going that way. Okay, exactly the same behavior as here. It was negative, so it started going to the left. So here it is negative, so it starts going to the left. Here it was positive, it started going to the right. Here it's positive, it starts going to the right. Okay, so what you have is this situation. So you go like this. And this is for t going to infinity. And this is also for t going to infinity. So this is what happens. And of course, if you, around here, you go in the opposite direction, meaning you take t going to minus infinity, then instead of going away, if you start from here, you will start coming to this point. Let me use some other color. Okay, I should have done slightly differently. Okay. So I showed that you get this behavior for t going to infinity. Okay, and this behavior for t going to minus infinity. Okay, so this is how things will behave when you are changing the value of t. This is how the running coupling will change. Okay, and now you see that these points are very special points, okay, because in t going to infinity limit or t going to minus infinity limit, you are reaching those points. So these points are called fixed points. So what's a fixed point? The value of the value GC, let's call it GC, of G bar. Okay, I'm using G now, at which the beta function vanishes is called a fixed point. Okay. Now there is a UV fixed point, ultraviolet fixed point. For example, G1 is an ultraviolet fixed point. Ultraviolet meaning T going to infinity. So in that limit, when you take large T, whether you start this way or that way, you are reaching the point G1. Okay, so G1 is a fixed point, and it's called an ultraviolet fixed point. Okay, G1 is ultraviolet fixed point. Because in T going to infinity limit, the coupling G bar goes to G1. Okay, and similarly you have infrared fixed point. So here T going to minus infinity, remember we had scaled by e to the T. Okay, e to the T. So when T goes to minus infinity, this is going to 0, right? So all the external momenta are really becoming very small, and that is what is called infrared. And and you see that here the behavior of this point G2 is, as you take T to minus infinity, okay, then you flow towards this value of G2. Okay, if you take T going to infinity, then you go away from it. Okay, you float to this point if T goes to minus infinity, and that is why it's called an infrared fixed point. Okay, there is a special case where the fixed point has a value GC, okay, like G1 or G2, where GC is 0. Okay, if that value is 0, then the theory is called asymptotically free. I'll tell you why. Okay, it's called asymptotic free, or the phenomena is called asymptotic freedom. So what is happening is that the running coupling becomes 0 in T going to infinity limit. Okay. So asymptotic means really in the limit T going to infinity. So that is where you are so you are approaching freedom. Freedom meaning free theory. You approach a free theory will have coupling constants as 0, right? There will be no interaction. So a free theory has no interactions. And because here you see, I'm looking at this vector right now, okay? Because if you calculate this Green's function, okay, using 0 couplings equal to 0, then you are basically calculating in a free theory. Okay, so if lambda bar goes to 0, you are basically in a free theory, and that is where from where you get this name, asymptotic freedom. Okay, so in T going to infinity limit, you are approaching free theory because the running coupling is 0. Okay, that's a fixed point, so G bar takes a value 0. So asymptotic freedom means running coupling G bar, okay, I'm still writing, goes to 0. Yes. Okay, that is GC equal to 0 is an ultraviolet fixed point. Okay, a given theory may or may not be asymptotically free. Okay, there are many theories which are not asymptotically free, and there are others which are asymptotically free. Okay, and that this, whether it is or not, it depends on the details of that theory. Okay, now I think I have already covered more than 1 hour. So, okay, next we will look at some implications of these fixed points in the next video. Okay, so that's what we will analyze in the next video. What do we learn from these fixed points? How theory, how Green's functions and other things behave when you are when you have a fixed point. Okay, and when you are close to the fixed point. Okay, see you in the next video.